I would like to start my talk with a survey. Who here, in a raise of hand, like to hike in snowy mountains? Please raise your hands. Let me see you. Okay, that's amazing. Thank you so much, because today we're going to talk a little bit about mountains, and more specifically about mountaintops and what is the best way to reach those. Actually, this is a photo of me hiking with some friends in the Matanuska Glacier in Alaska. Yes, Alaska. So how did I get to Alaska anyway? And why am I even sharing this with you? Let's start from the beginning. So, as mentioned, my name is Shir Meir Lador, and I'm a data science group manager at Intuit for almost 5 years now. For those of you who are not familiar with Intuit, Intuit develops an AI-driven expert platform that helps millions of customers, consumers, and small businesses overcome their most important financial challenges. Our mission is to power prosperity across the world, and we take this mission very seriously. You can imagine how sensitive is the data and the high stakes of the decisions we have to make with it. We at Intuit AI, as I mentioned, we take it very seriously. That's why we have published research about the topics of AI explainability and fairness, which I will share some of today. And we also decided to organize a workshop in KDD conference around these topics. And this conference took place in, who knows? Alaska, that's right. Yes, so this is how I got to Alaska. So in the workshop, we had the opportunity to host some of the leading experts and researchers in the field of AI explainability and fairness. One of them is the well-esteemed Professor Cynthia Ruding from Duke University. Don't know if you know about it, but she's really awesome. And following her keynote at the KDD conference that year, and the entire conference and workshop, I really got to realize that our role as data scientists is evolving. And what do I mean by that? Let me try to give you some context. I used to think, as the data scientist role, that we need to find the top model, right? We do everything to find the top model. I used to think about it like climbing a mountain. You start at the base, you understand the surface, understand the problem, collect the data sources, then you climb and climb up, you engineer your features, you select the right models, you tune them, do hyperparameter optimization, evaluation, and in the top of the mountain, you get to the model with the maximal accuracy or precision or recall or whatever metric you're trying to strive for. But can we really tell if there's only one accurate mountaintop for every problem we're trying to solve? And if the model that we are developing is used to make high-stake decisions that impact people's life, can we really tell if the model leads to a fair decision-making? Can we really tell if it gives similar treatment to similar people from different groups? On my flight to Alaska, I took this photo where you can see many, many mountains. And when I got there, I got to listen to the keynote of Professor Cynthia Ruding, which I mentioned earlier. And there, one of the main conclusions was that the space of optimal solution in many cases, by the way, this was a study in Rashomon theory in this paper. So the space of optimal solution is quite big, meaning that for each problem we're trying to solve, usually there can be multiple mountaintops. There could be multiple models, all with similar top performance, but they may have different characteristics. Some may be more complex, some may be more simple, some may use certain features, and some may use other features. We just need to think, are we choosing the best model to solve our problem? And how do we really define what is the best model? So in this talk, we will see how come that in the development stage, a model may seem optimal, but when you deploy it to production, it may in fact create discrimination. We will discuss how at the industry we can measure fairness, also in the literature, and we will see why it's really hard to understand what is objectively fair. We will propose a solution to create fair machine learning models, which are also accurate. And as a bonus, I will give you a take-home tool, Bias Detector, that would help each and every one of you data scientists to figure out whether the model is fair or not. So let's start with a few examples to where machine learning models can go wrong and lead to discrimination. The first example is the wide-known example of Compass. Compass is a model that, based on 137 questions answered by defendants in jail or pulled from their criminal records, trying to predict the likelihood of a defendant to reoffend in 2 years. It is used in US courts by judges, and the goal is to standardize the judge's decision. It was created in goodwill. But as you can see here below, the ProPublica study from a few years ago found that this model is actually discriminating because the false positive rate for African American defendants is twice as high than the false positive rate for white defendants. My second example is the gender shade study by MIT, which shows that top gender classifiers underperform for dark-skinned females. And the third example is the example from Apple Card credit limit. With this guy posted on Twitter how his wife got credit limit 20 times lower than he does, although they share the same household and the same income for many, many years. Many people replied to his tweet with their own example of a similar situation. This created a real Twitter storm. And you can see Apple's official response on this. They're saying that they're not using the gender in their decision-making. Okay, but if you think about it a bit, if they have my purchase history, well, using enough data, they can easily infer my gender from my purchase history, right? So that's not enough. They also said in their official response that some of the customers told them that they received lower credit lines than expected. In many cases, this is because the existing cards are under their spouse's primary account, which may result in the applicant having limited personal credit history, meaning that basically women which had joint bank account with their husband had a limited credit history and therefore got lower credit line. So let's try to gather all the reasons for discrimination by machine learning models, according to what we saw in the example. First, there's sample size dispersity. Machine learning models, as you probably know, try to optimize for overall or average accuracy, meaning that it tends to perform really well on the majority group in the data. And when there are minorities, sometimes it tends to slack on the minorities. And this is what we saw in the gender shade example, when the model underperformed for dark-skinned females because they were underrepresented in the data set. Secondly, feature information can be different for different groups, like what we saw in the Apple Card example, where women with joint bank account with their husband has missing credit history and therefore got discriminated with lower credit lines. Also, labels could be gathered in the biased way, like positive labels for loan approval, which may limit the model ability to explore new populations that don't usually get their loans approved. And lastly, labels are possibly a product of a bias system. So in this case, the model would just try to imitate the bad patterns they see in the data, and then the model would be biased as well. So before we continue, I would like to make an important definition that would help us afterwards in the talk. What are protected attributes? Protected attributes are qualities, traits, or characteristics like gender, race, or age that by law cannot be discriminated against. So one person once told me, one person I worked with, he told me, Shir, the most important thing you do when you develop machine learning model is do not use the protected attributes. The question is, can I really ensure that I'm fair in my model just by not using the protected attributes? What do you think? Yes. Well, you listen, that's good. The answer is no. Because, as I said earlier, some other features may be proxies to the protected attributes. So the question is, how can we find a way to systematically detect and mitigate those issues? The fairness literature tried to find different ways to measure fairness, and then through these metrics, we try to mitigate fairness in our models. So there are two types of fairness metrics, group fairness and individual fairness. Group fairness try to preserve the same score distribution on all the group. And you can see some of the common metrics here. For example, demographic parity, trying to preserve the same ratio of positive labeling within all the group in the dataset. So here is an example to where this could go wrong. Take, for example, a job application process for a software engineering role. And let's say that in the applicants, you have 80% male and 20% female. If we're trying to preserve group fairness, the same ratio from each group would advance to the next level. But maybe female applicants are generally more qualified, maybe. Well, in that case, achieving group fairness might hurt some individual women. So let's look at individual fairness, the other side of fairness metrics. Individual fairness trying to make sure that similar individuals from different groups or similar individuals in general should get similar scores. The challenge with, that sounds good, right? But the challenge with individual fairness is well, I'll say it in a minute. I'll just review some of the metrics. What we're trying to achieve in individual fairness is that the true positive rate and the false positive rate within the different groups would be similar. Like we saw, for example, in Compass, the individual fairness was hurt because the false positive rate for the Black defendants was higher than for other defendants. So the challenge, as I said, with individual fairness is how do we define who is similar? Is similar in one context the same as similar in another context? Is Euclidean distance is the right metric to define similarity? So we're understanding now that making a model objectively fair but by all the different metrics is hard because they sometimes even contradict each other. So what we propose is to try to aspire for less. Instead of trying to be objectively fair by all the possible metrics, we're trying to be fair in the specific context of the problem. We're aspiring for fairness by consistency. Our goal is to make the model consistent with our notion of fairness using examples. And the method I will just give the intuition for now is described more thoroughly in this published paper about pair consistency. It was published in ECML 2019 in the Data Science for Social Good workshop, and all of these great group of people from Intuit contributed to this. So let's try to understand the gist of it. We're trying to define consistency in order to achieve fairness. So we ask for a fair domain expert who understands the problem well to help us. We ask them to select pairs in the dataset, look in the dataset, and try to find pairs that should be classified together, but differ in at least one value of the protected variable. For example, in this data set of job applicants, again, we have the red pair. Both of them are paired by the expert because he or she thinks that they are not qualified enough to go to the next step. And they see that their gender is different. One is female and one is male. And the green pair are both classified together by the expert because they have enough experience to advance to the next level. Okay, so now we have two pairs defined by the expert, and our goal is basically for the model to agree, to be consistent with the expert's opinion by classifying those pairs together, although they are from different groups. Okay, this will help us eliminate discrimination between the group. That's the idea. And now we created a process which is very domain specific. Okay, these people are similar in the domain of the problem, but it is feature and model agnostic. It doesn't matter now what features we will use in the model and what kind of model we would choose to optimize. The only thing we care about is what would be the consistency of the model with our pairs, with the pairs we defined. So we can create a score with these paired. It's called the paired consistency score, which is basically the ratio of pairs having their members assigned to the same class. How much the model agrees with the expert opinion and classify our pairs together. And here, for example, the model classified the red pair not together. He advanced one of them and didn't advance the other to the next step. While the green pair was classified together. So in this case, the score is 0.5. And of course, we want the score to be as high as possible, 1 if possible. We can also formulate the score in the same manner for the regression case and also use it in regression problems. And now we got a way to monitor how consistent is the model with our notion of fairness just by using these pairs. So now what can we do with this score? Let me take you back to all of the possible top models that all perform similarly, but maybe a little different from one another. So we can use this score just for model selection, you know, and if we have all of these options, just take the one that have the highest consistency score. And the next stage would be, let's try to optimize for consistency in the optimization process, leverage the score within the optimization. So how would that look like mathematically? Well, we can just add a penalty regularization with the consistency score to our loss term. For example, here you can see the loss function, the mean square error, and we added a penalty including the consistency score and some kind of a regularization factor that determine how strongly we want to regulate for fairness. So now we're injecting more information. We're not just trying to optimize the loss function to be minimal loss. We're also trying to optimize the model to find the most consistent decision making with the expert. We did an experiment on the census income dataset to see how well are we actually achieving our goal, which is less relying on the protected attributes and not creating discrimination. So we took this dataset, which is widely known. It has 32,000 samples. It is based on demographic data, and based on that, we're trying to predict whether a person has a high or low income. There are a few protected attributes here. We used age for this experiment. And the other features are all kinds of life preferences of people. Based on that, we will predict the income. And we added the paired consistency penalty, the one we saw earlier, to the loss function of a decision tree and logistic regression. And let's see what happened. So what you can see here is as we increased their regularization, more trying to make the model more consistent, we can see that the age, the importance of the age in the decisions of the model decreased like we wanted, while the accuracy stayed roughly the same. You can see that we kept age as an input to the model in order to emulate what would happen in the real world, where we have proxies for the age with other features. So we're seeing we actually were able to find a model which is more fair, and the accuracy didn't change. It stayed the same. We also did another experiment by increasing the number of pairs we leverage in the consistency score. And again, we see that as we increase the number of pairs, the age was ranked lower and the accuracy stayed roughly the same. So in general, the regularization did not reduce the accuracy. So here are some conclusions so far. We saw that accurate machine learning models can possibly create discrimination if we don't check for that. We saw how it's challenging to define fairness objectively and how different fairness metrics can even contradict one another. And we proposed a method to find an accurate model which is both consistent and fair in the subjective notion of the problem. So now what? What can you go home with? How can you tell if the model you are developing is fair? Well, there are different tools in the industry that can help you detect whether your model is biased or not. The problem with this tool is that they all require the protected attributes. But usually, we don't have the protected attributes in the dataset. There are even some laws that prevent us from having them or from collecting this data. So what can we do? Well, imagine that you had a black box that you can give them the black box, you can give it the model scores and whatever information you do have about the user you're scoring. And that this black box could tell you whether your model is biased or not. Wouldn't that be great, right? Well, we thought it would be great, so we went on and developed it. And it's called the Bias Detector. Bias Detector is a very simple Python package. You can just pip install it very easily. And what it does, it can detect bias in machine learning models without using the protected attributes. And if you want to learn more about how it works, you can see the paper which was published lately, Bias Detection Using Name and Disparity Tables across protected groups. And it was published in the Journal of Responsible Technology in April. And was all of these great people contributed to it. And you can see that just by very simple 3 lines of code, you can get an answer to a question whether your model is biased or not. So just in general, how it works. You can provide it with you need to provide it the true labels and the model predictions. And then, as I said, you just give it whatever information you do have about the user, which is not a protected attribute. If you have only an email address, so you can give us the email address. And from the email address, we would extract the first name and the last name. If you already have the first and last name, then give us those. And if you have the zip codes are optional, you can also give it to us. It will add more information. And then based on the first name and the zip codes, we will infer probabilistically what is the probability for each of the gender and for each of the races in the data set. And based on these probabilities, we will calculate inferred bias metrics, like the metrics we saw before, which are not exactly by the same formula. It's the formula that leverages these probabilities, but it has the same meaning. And then we can answer the question, is the model biased? And is this result statistically significant or not? So I really encourage you to go and try this at home. And just to show you that it's worth it, I will show you an experiment we did with the Compass data set. As I mentioned earlier, we had a problem there with individual fairness, right? So let's see if the bias detector was able to detect these biases without knowing the race, which is in the data set. We just use the first name and last name. So yes, of course, the answer is yes, otherwise I wouldn't show it to you. The bias detector could detect the bias without using the race information. You can see here, this is one of the plots, the output from the bias detector. It gives a textual report and also a couple of plots. And this plot shows the false positive rate for different groups. This one shows the black versus others. And you can see that for the black defendants, the false positive rate was significantly higher than for other defendants. And this is just based on the first and last names of the defendants in the dataset without using the race information. I encourage you, go home and try it. It's very, very simple. So I want to summarize with an optimistic conclusion. With the increase of using machine learning models in the world for high-stake decisions, our role as data scientists is evolving. We now have the power to make decisions that impact people's life. And with great power comes great responsibility. That's right. We not only need to make sure that our models are fair, we also need to make sure that they lead to a fair decision-making. Now, I want you to remember that reality may be biased, but as you saw, machine learning and AI tools have the potential to correct for these biases. And we, as data scientists, have the power to make it happen. Thank you.